Alessandro Volta, renowned as the brilliant mind behind the invention of the electric battery, was a pivotal figure in the advancement of modern science, particularly in the field of electrochemistry. Born on February 18, 1745, in the town of Como, located in present-day northern Italy, Volta displayed an exceptional curiosity for natural phenomena from an early age. Although his family had aspirations for him to enter the legal profession, he was drawn to the study of physics and electricity, a passion that would define his entire life. Raised in a deeply religious and traditional environment, Volta's intellectual inclinations were nurtured in the classical schools of the time, where he excelled in scientific disciplines despite a lack of formal laboratory resources. His education was marked by a strong foundation in Latin and philosophy. Yet his independent experiments and voracious reading habit allowed him to develop a unique and practical understanding of emerging scientific ideas. This self-driven approach eventually led him to conduct groundbreaking work in electricity, an area of study that was still in its infancy during his youth. Volta's early experiments were focused on atmospheric electricity and the nature of electric charge. He developed an instrument called the electrophoresis in 1775, a device that generated static electricity, which quickly gained popularity in European laboratories. His work gained attention from other scientists, and he began corresponding with notable figures across the continent. As his reputation grew, Volta was appointed as a professor of physics at the Royal School in Como, and later at the University of Pavia, where he served for several decades. These positions allowed him to refine his theories and experiment with more sophisticated apparatus. In 1776, Volta made a remarkable discovery related to the flammable properties of methane gas. He successfully isolated the gas from marshes and conducted a series of demonstrations showing how it could be ignited, further solidifying his role as an experimental physicist of notable skill. These early achievements, while significant in their own right, were only the prelude to his most famous and transformative contribution to science. The intellectual turning point in Volta's career came as a response to the work of Luigi Galvani, a contemporary who had observed that frog legs twitched when touched by metal instruments, a phenomenon Galvani interpreted as animal electricity. Volta questioned this conclusion, proposing instead that the twitching was caused by the interaction of different metals, not by any intrinsic electrical force within the animal tissue. To test his theory, Volta conducted a series of meticulous experiments, eventually constructing a device composed of alternating layers of zinc and copper discs separated by pieces of cloth soaked in a saltwater solution. In 1800, he revealed what would later be recognized as the first true electric battery, known as the voltaic pile. This invention produced a steady, continuous current, revolutionizing the way electricity was understood and used. It demonstrated for the first time that electrical energy could be generated through chemical reactions, rather than solely by friction or natural sources, opening a completely new dimension for scientific exploration and technological advancement. Invention marked a fundamental shift in the study of electricity, enabling future discoveries and applications that were previously inconceivable. The voltaic pile provided a reliable source of electric current, facilitating experimental research in fields ranging from electromagnetism to electrolysis. It laid the groundwork for future innovations by scientists such as Michael Faraday and André-Marie Ampère, who would build upon Volta's legacy to further unravel the complexities of electric and magnetic forces. The battery also had practical implications, serving as a foundation for the development of electrical circuits, telecommunications, and eventually, portable energy storage. Volta's discovery received immediate acclaim, and he was invited by Napoleon Bonaparte to demonstrate his invention in Paris. Deeply impressed by the presentation, Napoleon awarded Volta several honors, including a gold medal and a Nobel title, and appointed him as a member of the French Institute. Volta's status as a national hero in Italy and a celebrated figure in European science was firmly established through this recognition. Despite his fame, Volta remained a reserved and methodical thinker who preferred the solitude of the laboratory to the spotlight of public attention. He continued to refine his battery design and published his findings in academic journals, always emphasizing empirical validation over speculation. His work was characterized by precision and a clear commitment to truth, driven by a genuine desire to uncover the principles governing nature. As a scientist, He was both meticulous and visionary, blending careful observation with theoretical insight in a manner that made his conclusions both robust and influential. Throughout his career, Volta contributed significantly to education, as well, mentoring young scientists and fostering a culture of inquiry and discipline. He held numerous academic and governmental posts, using his influence to promote scientific research and innovation in Italy. Even in positions of authority, he remained dedicated to the pursuit of knowledge and the advancement of public understanding of science. Volta's later years were marked by a gradual retreat from public life, as he increasingly withdrew from his academic duties to spend time with his family and continue private experimentation. Although he never ceased his intellectual pursuits, his pace of work slowed, and he began to focus more on writing and reflecting on his long and accomplished career. His health began to decline, a natural result of advancing age, but his mind remained sharp and engaged with the latest developments in science. His final years were spent in the quiet surroundings of his home near Lake Como, where he continued to enjoy reading, thinking, and maintaining a connection to the natural world that had inspired his early experiments. He passed away peacefully on March 5, 1827, at the age of 82, leaving behind a monumental scientific legacy that would endure for generations. His contributions to the field of electricity were not only foundational but transformative, setting in motion a chain of discovery and innovation that continues to shape the modern world. The name Alessandro Volta has since become synonymous with electrical science, and his influence is commemorated in numerous ways. The unit of electric potential, the volt, is named in his honor, a fitting tribute to the man who first made it possible to harness electricity in a controlled and consistent manner. Monuments, institutions, and academic awards bearing his name stand as lasting reminders of his achievements and the enduring value of his work. His impact extends far beyond the confines of his era, influencing technologies ranging from batteries in everyday devices to large-scale electrical grids that power entire cities. Volta's story serves as a powerful example of how disciplined inquiry, combined with creative thinking, can yield discoveries that transform the world. His legacy is not just one of invention but of inspiration, a beacon for scientists and innovators who strive to understand and improve the human experience. Through his life and work, Alessandro Volta illuminated the path toward a future powered by knowledge and driven by curiosity. James Clerk Maxwell one of the most brilliant theoretical physicists of the 19th century, fundamentally transformed the understanding of electromagnetism and laid the foundations for modern physics, with a legacy that continues to shape science and technology. Born on June 13, 1831, in Edinburgh, Scotland, Maxwell grew up in a quiet rural setting at his family's estate, Glenlyre, where his early life was filled with nature, exploration, and encouragement. From his intellectually curious father, tragedy struck early when his mother died of cancer when he was just 8 years old, leaving his upbringing largely in the hands of his father and a series of tutors. Demonstrating prodigious talent from a young age, he displayed a deep fascination with geometry and physical phenomena, crafting models and drawings that reflected a natural grasp of symmetry and form. At the age of 10, he had already written a paper on the properties of ovals, impressing scholars far older than himself. These early glimpses of genius foreshadowed the extraordinary contributions he would later make to science. Maxwell received his formal education at the Edinburgh Academy, where his intellect continued to flourish. Despite some social awkwardness and teasing by his peers due to his strong rural accent and quirky mannerisms, he remained undeterred, immersing himself in mathematics and natural philosophy. His academic excellence earned him a place at the University of Edinburgh, where he studied under some of Scotland's most respected scientists, and then at the University of Cambridge, where he joined Trinity College. At Cambridge, Maxwell quickly distinguished himself, winning the prestigious Smith's Prize in 1854 and later becoming a Fellow of Trinity. His early work included exploring the dynamics of Saturn's rings, where he demonstrated through mathematical reasoning that the rings could not be solid or liquid but must be composed of countless small particles, an insight later confirmed by space missions. His remarkable ability to blend complex mathematics with physical intuition set him apart and became a defining characteristic of his scientific career. Maxwell's most renowned achievement came in the field of electromagnetism, where he unified the previously separate disciplines of electricity and magnetism into a coherent theoretical framework. Building on the experimental findings of Michael Faraday, Maxwell developed a set of equations that described how electric and magnetic fields interact and propagate through space. These equations, now known as Maxwell's equations, showed that light itself is an electromagnetic wave, a revolutionary conclusion that linked optics to electromagnetism for the first time, by revealing that changing electric fields generate magnetic fields and vice versa. He provided the foundation for understanding how electromagnetic waves travel, forming the basis for technologies such as radio, television, and wireless communication. His insight that electromagnetic waves move at the speed of light was not only a triumph of theoretical physics but also a profound realization that light was a form of electromagnetic radiation. This conceptual unification of forces profoundly influenced the direction of physics and laid the groundwork for later developments in relativity and quantum theory. In addition to his groundbreaking work in electromagnetism, Maxwell made important contributions to the kinetic theory of gases. He introduced statistical methods into physics, proposing that the velocities of gas molecules follow a specific distribution, now known as the Maxwell-Boltzmann distribution. This statistical approach to understanding thermodynamics and molecular behavior helped establish the field of statistical mechanics, bridging the gap between macroscopic physical laws and microscopic molecular activity. His deep interest in color vision also led to important research in optics and perception. He constructed the first color photograph using the principles of additive color mixing, demonstrating how red, green, and blue light could be combined to recreate the visual spectrum. This achievement marked a major milestone in both scientific understanding and technological application, foreshadowing the development of color imaging systems. Maxwell's ability to traverse multiple domains of science with equal depth and originality underscored his status as a polymath and visionary thinker. Despite his immense contributions to science, Maxwell remained remarkably humble and deeply spiritual, often reflecting on the philosophical implications of natural laws. He was known for his kindness, integrity, and generosity as a mentor and teacher. Throughout his career, he maintained a balance between rigorous scientific inquiry and a contemplative respect for the mysteries of the universe. In 1856, he married Catherine Mary Dewar, who became a devoted companion and intellectual supporter. Their marriage was a source of great stability and comfort in his life. In 1859, Maxwell accepted the chair of natural philosophy at Marischal College in Aberdeen, and later held a professorship at King's College London, where much of his pioneering work on electromagnetism was conducted. He also became the first director of the Cavendish Laboratory at Cambridge, a role that allowed him to shape future generations of physicists and established one of the world's leading centers for experimental research. Though Maxwell's contributions were vast, his life was tragically short. In 1879, at the age of 48, he was diagnosed with abdominal cancer, the same illness that had claimed his mother. Despite intense pain and physical decline, he continued his academic duties and research as long as possible, demonstrating extraordinary resilience and devotion to science. He passed away on November 5, 1879, at his beloved Glenlair estate, leaving behind a monumental scientific legacy that would only grow in recognition with time. While he was highly respected during his lifetime, the full impact of his work became even more apparent in the decades that followed. Albert Einstein famously stated that the most profound event of the 19th century was Maxwell's discovery of the laws of electromagnetism, crediting those equations as a key inspiration for his own theory of relativity. The breadth and depth of Maxwell's scientific vision continue to influence modern physics, engineering, and information technology. James Clerk Maxwell's life and work represent the pinnacle of scientific creativity and analytical brilliance. His capacity to derive universal truths from abstract reasoning, combined with a commitment to clarity and elegance, made his theories not only powerful but enduring. The unification of electricity, magnetism, and light into a single framework was a profound leap in understanding that changed the course of science forever. His mathematical formulations provided a blueprint for the electromagnetic wave theory, which underpins much of contemporary communication and electronic technology. The continued relevance of his work in fields as diverse as telecommunications, quantum mechanics, and relativity is a testament to the foundational nature of his ideas. Maxwell's influence extends far beyond his own discoveries, shaping the very language and structure of modern physics. Today, James Clerk Maxwell is remembered as a towering figure whose contributions helped usher in the modern scientific era. Monuments, institutions, and scientific awards bearing his name reflect the high esteem in which he is held. His equations are inscribed on walls of laboratories, cited in textbooks, and celebrated as some of the most beautiful in all of science. More than a century after his death, his insights remain central to both theoretical and applied science. Maxwell's story is one of quiet genius, steadfast dedication, and profound curiosity, a narrative that continues to inspire scientists and thinkers across the world. Through a life guided by reason, imagination, and purpose, he illuminated the invisible forces that govern our universe and left a legacy that endures through the light of understanding he helped to kindle. Enrico Fermi, one of the most pivotal figures in 20th century physics, is best remembered for developing the world's first nuclear reactor and for his substantial contributions to both theoretical and experimental physics. Born on September 29, 1901, in Rome, Italy, Fermi demonstrated an extraordinary aptitude for mathematics and science from a young age. His father, an official in the Italian railways, and his mother, a schoolteacher, supported his intellectual growth, though it was Fermi's own relentless curiosity and drive that propelled him toward excellence. As a teenager, he immersed himself in physics, texts, and experiments, building devices and mastering complex theories far beyond his years. The tragic death of his older brother, when Fermi was just 14, had a profound effect on him, pushing him deeper into his academic pursuits. As a form of solace, this early focus eventually led him to the Scuola Normale Superiore in Pisa, where he excelled and completed his doctoral thesis on X-ray scattering with distinction. His teachers immediately recognized his genius, and he quickly rose through academic ranks to become a professor and a leader. In the rapidly evolving world of quantum physics, Fermi's early work in statistical mechanics and quantum theory earned him wide recognition across Europe. He developed what became known as Fermi-Dirac statistics, a fundamental concept describing the distribution of particles, such as electrons, that obey the Pauli exclusion principle. This framework was essential to the development of modern quantum mechanics and had far-reaching implications in solid-state physics, particularly in explaining the behavior of metals and semiconductors. While his theoretical contributions were groundbreaking, Fermi's exceptional ability to conduct precise experiments distinguished him from many of his contemporaries. He had a practical, hands-on approach and an uncanny ability to design simple, yet effective experimental setups that yielded significant insights. Throughout the 1930s, he led a team of physicists in Rome that conducted innovative research on the behavior of neutrons and their interaction with atomic nuclei. It was during this time that Fermi discovered that bombarding elements with slow neutrons could make them more likely to absorb the neutrons and undergo transformation, a revelation that would become central to nuclear science. In 1938, was awarded the Nobel Prize in Physics for his work on induced radioactivity, specifically his discovery of new radioactive elements produced by neutron bombardment. However, the political climate in Italy was becoming increasingly hostile due to the rise of fascism and the introduction of racial laws targeting Jewish citizens. Fermi's wife, Laura, was Jewish, and fearing for their safety, the family left Italy under the pretense of accepting the Nobel Prize in Stockholm. From there, they emigrated to the United States, where Fermi accepted a position at Columbia University. His arrival in America marked the beginning of a new phase in his career, one that would place him at the center of the most transformative scientific endeavor of the 20th century. With the discovery of nuclear fission in Germany, the global scientific community quickly realized the immense potential and danger of splitting atomic nuclei. Fermi, now in the United States, was ideally positioned to lead research into harnessing this phenomenon for both energy and military purposes. Fermi's most famous achievement occurred on December 2, 1942, beneath the bleachers of the University of Chicago's Stagfield, where he and his team initiated the first controlled, self-sustaining nuclear chain reaction. The experiment, known as Chicago Pilot 1, was the result of meticulous planning, engineering, and theoretical analysis. By stacking layers of uranium and graphite in a carefully calculated arrangement, Fermi demonstrated that a nuclear reaction could be maintained and controlled. This success proved that nuclear energy could be harnessed, opening the door to both power generation and weapon development. Fermi's calm demeanor and methodical nature were instrumental in the project's success, earning him the respect of his colleagues and superiors. This momentous event marked the birth of the atomic age and established Fermi as a central figure in the Manhattan Project, the secret wartime effort to develop nuclear weapons before Nazi Germany could achieve the same goal. During the war, Fermi continued to work on nuclear chain reactions and reactor design, contributing critical insights that guided the construction of reactors and the eventual development of atomic bombs. He moved to Los Alamos, New Mexico, to join other top scientists, working under Robert Oppenheimer, where he played a vital role in both theoretical planning and experimental testing. Fermi was involved in the Trinity test, the first detonation of a nuclear device, and witnessed firsthand the awesome power unleashed by the scientific knowledge he helped cultivate. Though instrumental in the development of nuclear weapons, Fermi was deeply reflective about the implications of his work. He later advocated for international control of atomic energy and promoted peaceful uses of nuclear power. His moral clarity and scientific integrity remained intact, even as the world grappled with the consequences of atomic technology. After the war, Fermi turned his attention back to academic research and education, becoming a professor at the University of Chicago. There, he founded the Institute for Nuclear Studies, which would become one of the leading centers for advanced physics research in the world. Fermi continued to publish influential papers and mentor a generation of scientists, many of whom went on to win Nobel Prizes themselves. His teaching style was admired for its clarity, simplicity, and rigor, earning him a reputation as both a great scientist and a great educator. He emphasized physical intuition and the importance of approximation techniques, which became hallmarks of what later came to be known as Fermi problems, simple estimations used to analyze complex situations. His combination of theoretical brilliance and experimental pragmatism made him a model for future physicists and a bridge between the abstract and the practical. Fermi's health began to decline in the early 1950s, and he was diagnosed with stomach cancer, an illness that progressed rapidly. Despite his deteriorating condition, he remained engaged with his work and continued mentoring students until he could no longer physically do so. He underwent surgery and treatment, but the disease proved incurable. On November 28, 1954, Enrico Fermi died at the age of 53 in Chicago, leaving behind a legacy that reshaped physics, engineering, and global geopolitics. His death was mourned by the international scientific community, which recognized him not only as a master of his craft, but also as a figure of rare integrity, humility, and vision. In his honor, Fermilab, the United States' premier particle physics laboratory, was named after him, ensuring that his contributions would be remembered by generations of scientists. His name was also immortalized in Element 100, Fermium, further cementing his place in scientific history. Enrico Fermi's influence extends far beyond the laboratory, resonating in fields as diverse as nuclear medicine, energy policy, astrophysics, and environmental science. His work on the first reactor made the peaceful use of nuclear energy possible, while his insights into fundamental particles laid the groundwork for modern quantum field theory and the Standard Model of particle physics. His ability to seamlessly transition between theory and experiment, his calm leadership during moments of historical importance, and his commitment to the responsible use of scientific knowledge define him as one of the greatest minds of his era. Fermi's story is not just one of scientific triumph, but also one of ethical responsibility, intellectual curiosity, and a lifelong pursuit of understanding the universe. His contributions continue to guide scientific thought and inspire those who seek to explore the unknown with rigor, courage, and compassion. Werner Heisenberg. Werner Heisenberg, a towering figure in the realm of 20th century physics, is most famously associated with the formulation of the uncertainty principle, a fundamental concept that reshaped the understanding of quantum mechanics and the behavior of subatomic particles. Born on December 5, 1901, in Würzburg, Germany, Heisenberg grew up in an academically enriched environment. His father was a professor of Greek philology, and the atmosphere in their home encouraged intellectual curiosity and cultural awareness. From an early age, Heisenberg exhibited a remarkable talent for mathematics and problem-solving. He pursued his higher education at the University of Munich, where he studied under the distinguished physicist Arnold Sommerfeld. Sommerfeld's mentorship introduced Heisenberg to the latest developments in atomic theory and the complexities of spectral lines, which would become central to his future work. Early in his academic journey, Heisenberg stood out not only for his exceptional grasp of abstract mathematics, but also for his deep interest in the philosophical implications of physical laws. This blend of scientific rigor and philosophical contemplation became a defining feature of his approach to physics. In the early 1920s, Heisenberg began collaborating with some of the leading physicists of the time, including Niels Bohr, whose Copenhagen Institute served as a hub for innovative thinking about atomic structure. While working with Bohr, Heisenberg delved into the limitations of classical mechanics in explaining atomic behavior and began developing new theoretical models. In 1925, at the age of just 23, he introduced matrix mechanics, an entirely novel formulation of quantum theory that replaced classical notions of motion with abstract mathematical constructs. This work, published in collaboration with Max Born and Pascal Jordan, laid the foundation for modern quantum mechanics. A year later, Heisenberg formulated the uncertainty principle, asserting that it is impossible to simultaneously determine both the exact position and momentum of a particle with absolute precision. This principle was not a result of experimental limitation, but an intrinsic property of nature at the quantum scale. The uncertainty principle challenged traditional deterministic views and introduced the new paradigm in physics where probability and measurement took center stage. Heisenberg's breakthrough had profound implications for both physics and philosophy. It signified a departure from the Newtonian worldview, in which all phenomena were thought to follow predictable, deterministic laws. Instead, it revealed that at the quantum level, reality could only be described in terms of probabilities, and observation itself influenced the state of the system. This revolutionary insight sparked widespread debate and redefined the boundary between what could be known and what remained inherently uncertain. Heisenberg's work quickly gained recognition, and in 1932 he was awarded the Nobel Prize in Physics for the creation of quantum mechanics, a system that had far-reaching applications in atomic and subatomic physics. His contributions helped shape the intellectual architecture of the quantum world, influencing generations of physicists and leading to the development of technologies such as semiconductors, lasers, and nuclear energy. Despite his youth, Heisenberg was acknowledged as one of the principal architects of modern theoretical physics, his name inseparable from the most fundamental aspects of quantum theory. As his academic reputation grew, Heisenberg accepted a professorship at the University of Leipzig, where he continued his research and became an influential teacher. He cultivated a vibrant intellectual environment, attracting young physicists from across Europe and contributing to the flourishing of theoretical physics in Germany. During the 1930s, as the political situation in Germany darkened under the rise of the Nazi regime, Heisenberg's position became increasingly complex. He was not a member of the Nazi Party, nor did he publicly endorse its ideology, but he chose to remain in Germany during this tumultuous period. When the Nazi government began promoting German physics, a nationalist and anti-Semitic movement that rejected theories developed by Jewish scientists like Albert Einstein, Heisenberg found himself under suspicion. He defended the legitimacy of modern physics and quantum theory at great personal risk, enduring smear campaigns and political attacks. His resilience during this time reflected both his commitment to science and his efforts to maintain a degree of academic integrity. In an environment increasingly hostile to intellectual freedom, during World War II, Heisenberg was placed at the head of Germany's nuclear research program, a position that has sparked ongoing historical debate. Leading the Uran-Varine or Uranium Club, he worked on nuclear fission and the theoretical possibilities of an atomic weapon, unlike the Manhattan Project in the United States, which successfully developed the atomic bomb. The German program under Heisenberg never produced a functional weapon. Historians have argued over whether this failure was due to technical limitations, lack of resources, or a deliberate moral stance on Heisenberg's part. He claimed after the war that he had no intention of creating a nuclear bomb for the Nazis, but this assertion remains a subject of scrutiny and interpretation. What is clear is that Heisenberg continued to focus on the theoretical aspects of nuclear reactions and energy production, while avoiding involvement in direct weapons design. His wartime role remains one of the most complex aspects of his legacy, reflecting the difficult ethical terrain navigated by scientists during periods of political extremism. After the war, Heisenberg was briefly detained by Allied forces as part of Operation Epsilon, which aimed to determine the progress of the German nuclear project and the intentions of its leading scientists. He was held in England with other prominent physicists and monitored during their conversations. The transcripts of these conversations revealed a mix of scientific discussion, personal reflection, and bewilderment upon hearing of the atomic bombings in Japan. Following his release, Heisenberg returned to Germany and became instrumental in rebuilding scientific institutions that had been dismantled by the war. He took a leading role in the establishment of the Max Planck Institute for Physics in Göttingen and later in Munich, serving as its director and working to revive the reputation of German science on the global stage. He also played an active part in promoting peaceful uses of atomic energy and advocated for international cooperation in scientific research, expressing a strong belief that science should transcend national boundaries and political divisions. In his later years, Heisenberg continued to explore fundamental questions in physics, including attempts to unify quantum mechanics and general relativity. He proposed theories of a unified field and sought deeper understanding of particle interactions. Although these later efforts did not achieve the same impact as his earlier work, nevertheless, his intellectual curiosity and commitment to theoretical exploration remained undiminished. He engaged in public lectures, wrote extensively on the philosophical implications of quantum theory, and maintained correspondence with leading scientists around the world. Despite the controversies surrounding his wartime activities, he was widely respected for his scientific brilliance and his efforts to promote ethical responsibility in research. He remained an influential figure in both academic and cultural circles in post-war Europe, a symbol of Germany's scientific heritage and its efforts to reconcile with a difficult past. Werner Heisenberg's health began to decline in the 1970s, and he eventually succumbed to cancer. He died on February 1, 1976, in Munich at the age of 74. His death marked the passing of one of the last great pioneers of 20th century physics, a man whose work helped redefine the fundamental nature of reality. He was buried in the Waldfriedhof Cemetery in Munich, and his legacy was honored by scientific institutions around the world. His name lives on in the Heisenberg uncertainty principle, a cornerstone of quantum mechanics taught in every physics curriculum, as well as in countless books, research papers, and philosophical discussions. His approach to science, which combined mathematical precision with deep philosophical insight, continues to inspire those seeking to understand the complexities of the universe. Werner Heisenberg's life embodied the journey of science through one of the most turbulent eras in human history, a journey marked by brilliance, controversy, and an enduring quest for knowledge. Max Planck, a towering figure in the annals of modern physics, is universally recognized as the founder of quantum theory, a revolutionary development that transformed the understanding of energy, matter, and the fundamental laws of nature. Born on April 23, 1858, in Kiel, Germany, into a family of scholars and intellectuals, Planck was exposed early to a culture of education and rigorous thought. His father was a professor of law, and several of his relatives held academic positions, instilling in him a deep respect for scholarly discipline. Moving to Munich during his youth, Planck enrolled in the Maximilian Gymnasium, where he demonstrated a prodigious aptitude for mathematics and physics. Despite initial uncertainty about which academic path to pursue, he ultimately gravitated toward theoretical physics, finding in it a realm of structured reasoning and immutable principles that resonated with his methodical nature and philosophical disposition. After completing his university studies at Munich and Berlin, he earned his doctorate in 1879 with a thesis on the second law of thermodynamics, a subject that would guide much of his early career. Planck's early professional years were marked by a dedication to the study of heat and entropy, areas that were already well trodden by the scientific community but still held unresolved mysteries. Appointed as an associate professor at the University of Kiel, and later a full professor at the University of Berlin, Planck developed a reputation for his careful reasoning, precise language, and conservative approach to scientific innovation. Yet it was precisely his attention to thermodynamic theory that led him to a startling and unprecedented conclusion. In 1900, while investigating blackbody radiation, the phenomenon of electromagnetic radiation emitted by a heated object. Planck proposed that energy could only be emitted or absorbed in discrete quantities, which he called quanta. This contradicted the classical assumption that energy varied smoothly and continuously, challenging a core belief held by physicists for centuries. His formula, EHF, where E is energy, H is Planck's constant, and F is frequency, introduced a new fundamental constant to physics and planted the seed for the quantum revolution. Although initially met with skepticism, Planck's quantum hypothesis was soon validated by experimental results and found utility in explaining phenomena that had confounded classical physics. His discovery laid the groundwork for subsequent developments in quantum mechanics and influenced some of the greatest minds of the century, including Albert Einstein, Niels Bohr, and Werner Heisenberg. Einstein's work on the photoelectric effect further expanded on Planck's ideas and won him the Nobel Prize, a testament to the far-reaching implications of quantized energy. In 1918, Planck himself was awarded the Nobel Prize in Physics for his role in the origin and development of quantum theory. Despite the revolutionary nature of his work, Planck remained a reserved and philosophical figure, often reflecting on the deeper implications of the unpredictable and probabilistic world that quantum mechanics revealed. He believed deeply in the harmony of natural laws and maintained a steadfast conviction in the unity of science and rational thought. Throughout his career, Planck was revered not only for his scientific contributions, but also for his moral character and leadership within the academic community. He served multiple terms as president of the Kaiser Wilhelm Society, where he advocated for the integrity of science and the protection of intellectual freedom, especially during periods of political upheaval. During World War I, and later under the rise of the Nazi regime, Planck attempted to shield his colleagues from persecution and worked to preserve the independence of scientific institutions. His efforts were courageous but often fraught with difficulty as the political environment grew increasingly oppressive. Planck opposed the exclusion of Jewish scientists from academic life and pleaded with government officials to recognize the damage such policies inflicted on Germany's scientific reputation. His quiet resistance stood in stark contrast to the prevailing tide of conformity and repression, reflecting his deep personal commitment to ethics, humanity, and the sanctity of knowledge. The personal toll of these years was immense. Planck experienced profound personal tragedies, losing his first wife to illness and 3 of his 4 children under heartbreaking circumstances. His twin daughters died during childbirth, and his eldest son was killed in World War I. The deepest blow came in 1945, when his surviving son, Erwin, was executed by the Gestapo for his involvement in the failed July 20th plot to assassinate Adolf Hitler. This loss, compounded by the destruction of his home and much of his work during the war, left Planck in sorrow during his final years. Despite these immense personal losses, he continued to promote science as a force for peace and renewal, embodying a stoic resilience and unwavering belief in the power of reason. Even in the face of unimaginable grief, he remained an active figure in rebuilding German scientific life after the war, helping to restore institutions that had been torn apart by conflict and ideology. Max Planck's scientific legacy extends far beyond the equation that bears his name. His constant H became one of the most important quantities in physics, appearing in nearly every formulation of quantum mechanics and serving as a bridge between energy and frequency. The introduction of quantization redefined the understanding of atomic and subatomic processes and opened the door to discoveries such as wave-particle duality, quantum tunneling, and the uncertainty principle. Fields like quantum computing, nuclear energy, and semiconductor technology all traced their origins back to the foundations he laid. His philosophical writings on science and faith continue to inspire those who seek to understand not just how the universe works, but why it behaves as it does. His view that science and spirituality need not be in conflict, but rather could coexist in the pursuit of truth, remains a thoughtful contribution to the dialogue between empirical inquiry and metaphysical reflection. In recognition of his immense contributions, Planck's name has been immortalized in numerous ways. The Max Planck Society, founded as a successor to the Kaiser Wilhelm Society, is today one of the world's leading research organizations, with institutes across Germany and abroad dedicated to cutting-edge scientific exploration. His work is honored in fundamental constants, scientific literature, and the education of students who were introduced to his theories in physics classrooms around the globe. The Planck satellite, launched to study the cosmic microwave background radiation, bears his name in tribute to his pioneering role in uncovering the mysteries of the universe. These honors reflect not only his scientific genius, but also the respect he earned through his humility, perseverance, and unshakable dedication to the pursuit of knowledge. Max Planck died on October 4, 1947, at the age of 89, in Göttingen, Germany, after a life marked by both extraordinary achievement and profound sorrow. His death marked the end of an era in physics, but the ideas he introduced continue to resonate in the fabric of modern science. He is remembered not just as a discoverer of quantum theory, but as a symbol of integrity in science, a thinker who never wavered in his belief in the power of reason and the necessity of truth. His work transformed the way humanity understands nature, light, and matter, and his example continues to guide those who dedicate themselves to uncovering the secrets of the universe. Through his writings, teachings, and discoveries, Max Planck remains a guiding light for physicists and philosophers alike, a reminder that even the most abstract ideas can change the course of human history when pursued with clarity, courage, and conviction. Antoine Lavoisier, widely regarded as the father of modern chemistry, revolutionized scientific thought in the 18th century by introducing a new approach based on meticulous experimentation, logical reasoning, and the systematic measurement of chemical reactions. Born on August 26, 1743, in Paris, France, into a wealthy and influential family, Lavoisier received an excellent education that combined classical studies with exposure to the scientific advancements of his era. He showed early promise in mathematics and the natural sciences and chose to pursue a career in chemistry and law. Though he completed a law degree, his passion for scientific discovery soon overtook his legal ambitions. His early research into geology and atmospheric phenomena earned him recognition from the French Academy of Sciences, where he became a member at the unusually young age of 25. Lavoisier's scientific journey was marked by a clear determination to reform and elevate the field of chemistry from a collection of mystical theories and alchemical traditions to a rigorous, evidence-based discipline grounded in experimentation. Throughout his career, Lavoisier displayed a tireless dedication to accuracy and clarity, emphasizing the importance of measurement and reproducibility in chemical studies. He introduced the use of the balance as an essential tool in the laboratory, allowing him to measure mass with unprecedented precision. By doing so, he confirmed that matter is neither created nor destroyed in chemical reactions, thus formulating the law of conservation of mass, a foundational principle in modern science, rejecting the flawed phlogiston theory, which claimed that a fire-like element escaped during combustion. Lavoisier demonstrated that combustion involves the chemical combination of a substance with oxygen. This breakthrough fundamentally changed the understanding of burning, respiration, and oxidation, replacing vague speculation with concrete evidence and logical explanation. He also redefined the role of air in chemical reactions, showing that air is not a single substance but a mixture, mainly of nitrogen and oxygen, and that only the oxygen component is active in combustion and life processes. Lavoisier's work extended beyond theory to practical applications that improved public health, industry, and agriculture. His studies on water revealed that it is not an element, as previously believed, but a compound composed of hydrogen and oxygen. This overturned centuries of accepted thought and reshaped the basic classification of substances. He also played a major role in developing a systematic chemical nomenclature, creating a naming convention that clearly identified substances based on their composition and reaction behavior. This new language of chemistry helped eliminate confusion caused by inconsistent or redundant terminology and made scientific communication more accessible and precise. Collaborating with other leading scientists of the time, Lavoisier published a textbook titled Traité élémentaire de chimie élémentaire, Treatise of Chemistry in 1789, which outlined his discoveries and redefined the teaching of chemistry. The treatise laid out the principles of chemical reactions, introduced the concept of elements as fundamental building blocks, and described experiments with clarity and detail that allowed others to replicate and verify his results. In addition to his scientific work, Lavoisier was deeply involved in public service and government affairs. He served as a tax collector in the Ferme General, a private agency tasked with collecting taxes on behalf of the crown. Though controversial, this position funded his research and gave him access to resources and political connections. He used his influence to promote agricultural reform, improve urban sanitation, and study food production and nutrition. Lavoisier also contributed to France's economic and educational development, advocating for the standardization of weights and measures, which laid the groundwork for the metric system. He believed that scientific knowledge should benefit society and worked tirelessly to apply his discoveries to real-world challenges. His commitment to rationality, order, and empirical evidence earned him admiration from fellow scientists, but also exposed him to political hostility during times of social unrest and revolutionary fervor. As the French Revolution intensified, Lavoisier's association with the old regime and his role as a tax official made him a target of suspicion and resentment. Despite his scientific achievements and his efforts to use science for the public good, he was arrested during the Reign of Terror, along with other members of the firm Reactor. Attempts to intervene on his behalf were unsuccessful, and his trial was swift and politically charged. On May 8, 1794, at the age of 50, Antoine Lavoisier was executed by guillotine in Paris. His death shocked the scientific community and was widely regarded as a tragic loss to human knowledge. The mathematician Joseph-Louis Lagrange famously remarked that it took only a moment to cut off a head that was 100 years in advance of its time. Despite the violent and untimely end to his life, Lavoisier's legacy endured and grew in the centuries that followed, cementing his status as a pioneer who laid the foundation for modern chemical science. The impact of Lavoisier's work cannot be overstated. His insistence on quantitative methods introduced a level of discipline and predictability to chemistry that aligned it with the physical sciences. He transformed the study of chemical reactions from a speculative art into a precise and systematic investigation of matter and its transformations. His approach influenced generations of chemists and physicists and shaped the scientific method itself. The tools, techniques, and terminology he introduced remain in use today, and his experiments continue to be replicated in classrooms and laboratories around the world. He showed that through observation, measurement, and rational thought, even the most complex natural processes could be understood and explained. His vision of chemistry as a coherent, universal science paved the way for countless discoveries in fields ranging from medicine to environmental science, and continues to guide scientific inquiry to this day. Lavoisier's life and work embody the power of human reason and the pursuit of knowledge, even in the face of political upheaval and personal danger. His contributions were rooted in a deep belief in progress, education, and the shared advancement of civilization through science. He demonstrated that truth must be tested and proven, not accepted by tradition or authority alone. His story is a reminder that intellectual courage and moral conviction often carry great risk, but that the pursuit of truth remains among humanity's highest callings. From his laboratory in Paris to the farthest reaches of modern scientific thought, the influence of Antoine Lavoisier endures, a testament to one man's extraordinary dedication to uncovering the laws that govern the natural world. His legacy, as the father of modern chemistry, is not merely a historical title, but a living force that continues to inspire and inform the scientific journey of generations past, present, and future.